This is the lecture video for Chapter 3, Objective 7, so optimization problems for AP Calc BC. So what we're going to be looking at is we're going to be looking at maximizing and minimizing, but in terms of word problems. So just kind of a reminder of how we find maximum and minimums in terms of calculus component is we would find our critical numbers, right? So we would find our critical numbers. So we would set f prime equal to 0 and also look for excluded values, so where it would be undefined. And then we would do a number line sign analysis. To determine if we have a maximum or a minimum. Okay, so just in general, like that's how we would find maximum and minimum values. So for us, because we are working with word problems, we want to make sure that we kind of follow a certain path, though, to get to that correct answer. So what we want to make sure that we always do is we assign variables to all of our given quantities and those to be determined. Okay, so that way we know ahead of time, like what are we going to call X, what are we going to call Y, and then if we can, we want to make a sketch for that as well. And then in the solving process, we're going to have what we call a primary equation. And how we will know that we're working with a primary equation is that it will tell you specifically like maximize or minimize. So if they want maximum area or minimum volume or something like that, then that is what our primary equation is. And that is the equation we will take the derivative of because that's the one we're trying to maximize. Okay? And then our secondary equation, if we need this is not always needed, is to reduce the primary equation to a single independent variable through substitution. So if when we write out our primary equation, we have more than one variable, so like maybe volume is equal to pi r squared h, we're going to use our secondary equation to replace either r or h, very much like what we did with related rates. And then after we do that substitution, if that's needed, then we will go ahead and find either our max or minimum value, and we're going to use calculus. So again, we'll be doing this f prime equal to 0. And then find the number line sign analysis as well. Okay, so you're going to want your graphing calculator because we will use that throughout. Okay, so we have two examples here we're going to work through. Okay, so the first one is we're going to have a Norman window, and that is constructed by adjoining a semicircle to the top of an ordinary rectangular window. Okay, so I'm going to go ahead and draw a picture of that. So we have some sort of rectangular window, whatever that happens to look like. And then we have a semicircle on top of that. So something like that. Not the best, but there you go. Okay. And we want to find the dimensions of the window of maximum area. So we're trying to maximize area. And so that means this will be our primary equation. So the area formula will be our primary equation. And then we're given that the total perimeter is 20 feet. So we're going to start with just that primary equation component because that's what we're going to be taking the derivative of. So we need to figure out, all right, so what am I going to call what? And it really doesn't matter what letters you use. So you can use x's and y's, bases and heights, you know, whatever it is that you want to use for that. So I would start out with like maybe the, rectangle has a base called x, and then this height would be y, right? And so I'm going to have to do area, so that would be like all of this. So I'm going to need something to help me find area of the semicircle. So I need radius, right? So if all the way across from here to here is x, then this would be 1/2 x. Okay, so that's what I could certainly do. So when I look at that, like one of the things I'm looking at is I'm like, oh geez, I'm gonna have to work with fractions here, which like that's not the end of the world, of course. But what I'm gonna do just a little bit different so I can maybe avoid those fractions is I'm gonna say, all right, so like, well, that's all good. But what if instead of doing something like that, so instead of that, what if I take a look at my picture like this instead? So again, I'm going to do my rectangle and my semicircle across the top. So what if instead I'm going to say, all right, let's call my radius x. And then all the way across would be 2x. and then I'm still going to go ahead and call my height y. I would get the same exact answer if I worked with it this way or this way, and it really doesn't matter, but over here I'm like, oh, you know, 2x versus 1/2 x, why not? All right, so let's go ahead and write out what would be my primary equation. So I'm just going to use PE for primary equation, and I know that it has to be the area formula of this right here. So my area would be of the rectangle base times height, so base times height, so that would be 2xy, and then plus the area of a semicircle. Well, the area of a whole circle is pi r squared, but that's just half of a circle, so that would be 1/2 pi, and then my radius is x, so 1/2 pi x squared. Okay, so that's my primary equation. Okay, so again, area of this rectangle right here, so base times height, so 2x times y. And then I also need to add in the area of the semicircle, so 1/2 pi r squared, but my radius I called x. So then what I look at is, do I need a secondary equation? And I look over here and I see, well, yeah, I do, unfortunately, because I have two variables here, right, two variables. And so I need to get this down to 1. And so I need to use a secondary equation. So I'm going to go ahead and just do that off to the side, since I'm not really going to use any calculus with it. I'm just going to use it for substitution purposes. So I'm just going to write SE for secondary, and then I'm going to use it to substitute over here. So if I keep reading, I see that perimeter is 20 feet, right? So the total perimeter is 20 feet. So that gives me more information that I can utilize to create a secondary. So my perimeter is 20 feet. So I'm going to just use 20 feet for my perimeter. And that's of the window, right? Perimeter of the window. So that would be all the way around the window. So around the window, so I would have y, 2x, and y. So that would be 2x on the base, and then y here. So that would be plus 2y. And then plus this outside. So this is not part of the perimeter right here, right? That's not the exterior amount. So my perimeter here. So that is circumference, right? So circumference is normally 2 pi r, of like all the way around, but we're only going halfway around. So half of the circumference, so take half of that. So half of the circumference would be just pi r. Okay, so that would be plus pi, and then r being my x. So if I'm using that to replace, I can replace either x or y, it doesn't really matter. So if I look at this, it looks easier to solve for y, and it looks like it would be easier to substitute it in here as well. So I'm going to go ahead and isolate and solve for y. So I'm going to subtract 2x and pi x to the other side. And I'm going to drop my units here just for ease. So subtract 2x and subtract pi x. And then divide everything by 2. So I will get y is equal, and then I'm going to go ahead and divide here. So 20 divided by 2 is 10. And then 2 divided by 2 is 1, so negative 1x. And then minus 1/2 pi x. And so now I'm going to take this value for y and substitute it into this value of y. And then that way I'll get my equation in terms of all of x's. So I would have a equals 2x, and then replace my y, so this is y here. So that's 2xy, and then plus 1/2 pi x squared. And then once I get here, my goal is to take the derivative and equal it to 0. So this is kind of messy, which is fine. Like, I could totally take that derivative, but I want to kind of clean it up. So the cleaner my original function is, the more friendly my derivative will be. So I'm going to go ahead and distribute the 2x in, just so I can kind of clean things up a little bit. So this is still a. So that would be 20x minus 2x squared minus, so half of 2 is just 1, so that would be pi x squared, and then plus 1/2 pi x squared. And then I can combine these terms together because they both are a pi x squared, or some portion of that. So this would be negative 1 pi plus 1/2 pi, so that would be negative 1/2 pi and then x squared. So there's a much friendlier form. So then once I get to here, I'm going to go ahead and take the derivative, and so I'm going to take that derivative with respect to x. And again, I'm doing that because I'm looking for the maximum area, right? Maximum area. So I want to take the derivative, equal it to 0 to find my critical numbers. So that would be a prime, or dA over dx. And then the derivative of 20x would be 20x to the 0, so just 20. And then minus 4x, and then multiply down the 2, so half of 2 is 1, so what would that be? Negative pi x. And then set that equal to 0. And then go ahead and solve that to find your critical numbers. So I'm going to add these two to the other side, just so that you don't have so many negatives. And then I can factor an x out of both of those. And then divide. All right, and so typically like that would be like, you know, we're good, but, and you are welcome to leave it in that, but I'm going to go ahead and just make that a decimal value just for sake of, you know, conversation. Like that would be a whole lot easier to say than 20 divided by 4, the quantity of 4 plus pi. And so I get 2.800, and then that was in feet. And then I still need to know what y equals, right? So there is my x because it asked for the dimensions. So there's the value of x, but I still need to find the value of y. So there's one of my answers. And so now to find my y value, I'm going to go ahead and substitute that into there. And then work through that just a little bit, not a lot. So half of 20, so that would be 10, so minus. And then I'm on my calculator right now. And so I get y is equal to 2.800 feet as well. So that's about equals. Okay, so there are my x and my y values. And so then now the directions we're asking for your dimensions, right? So let's look at that picture real quick. So for your dimensions, that would be like your base and your height. So I know my radius was x, right? So this distance here, x was 2.8, and I know the height was 2.8, but I need to know like the whole dimension, so I need to know that entire base. And so then my base would be double this, right? So my base would be double that value because I need to go all the way across. So my base would be that times 2. So that would be, I can have it as a decimal or the exact value, either one. So I'm going to just truncate, so that would be feet. And then my height, so the height of the rectangular window, would be the y value, which was 2.800 feet. And so that would actually be what my answer is, right? My base and my height would be that. Okay? All right, so let's go ahead and take a look at one more example here. All right, so we have a rectangle that is bounded by the x and the y axis, and then the graph of y equals 8 minus x all divided by 2. So let's just get a picture of that component here before we get the whole graph. So I'm going to just start with that equation, y equals 8 minus x divided by 2. And I'm going to put it more in a format that I'm used to seeing, like a slope linear kind of equation. So I'm going to go ahead and divide both pieces by 2. So 8 divided by 2 is 4. And then x divided by 2 would be 1/2 x. And so just rewrite that so it's in that proper form, negative 1/2 x plus 4. So let's go ahead and graph what we have so far. So 1/2 x plus 4. So I have a y-intercept of 4. So when x is 0, y would be 4. And then a slope of 1/2, so I would be going down 1 and then over 2. And then down 1 over 2. So wait, what would be my, so when x is 0, y is 4. When y is 0, I'm going to do some math here so I don't have to work so hard. Negative, that would be negative 8. 7, 8. So this is not a straight line. I should have done this on graph paper. Pretend that's a straight line, everybody. Okay, so what I know is that it crosses at 4 and crosses at 8. If I go down 1 over 2 enough times, or just let y equals 0 and solve for x, and that's what I did there. Okay, so there's my lovely straight line. All right, so now we have a rectangle that is bounded by the x and the y axes. So here's my x and my y axes, so bounded by that, and this graph. So whatever that looks like, right? So we don't know for sure where that would cross or like what it would look like, so I'm just going to do kind of a random point right here. So we'll say that's the rectangle that we're talking about. And I don't know where this is crossing. We'll just say it's crossing at some random point x comma y. And so I don't know where on the x it is or where on the y, right? So that's at some random point. And it's asking for what should the length and the width be so that the area is maximum. So I'm trying to maximize area again, right? Maximize area. So that will be my primary equation, right? So my primary equation is going to be area, because that's what I'm maximizing. So I'm just going to write primary equation. So the area of this rectangle then, it would be base times height. So the base would be wherever we are on the x-axis times the height wherever we are on the y. So area is equal to xy. So then I have to decide, okay, do I need a secondary equation, yes or no? And that would be yes, right? Because I have, you know, two variables, right? An x and a y. So I do have to create another equation. Well, the nice thing is we have it right here, right? So our secondary equation actually kind of fell out of the problem by us trying to find that graph and that line. So that is already my secondary equation, which was kind of done for us, which was lovely. So now I'm going to use that equation for y and replace that into here. So then my area would be equal to x times y. And then again, I'm going to clean this up before I take the derivative. So I'm going to distribute that x in. And then now I'm going to go ahead and take that derivative with respect to x so I can find my critical numbers. And so then I would have a prime, or dA over dx, and then 2 times negative 1/2 is negative 1x, and then 4x to the 0, which would just be 4. And then now set that equal to 0. So subtract 4 and divide by negative 1. So I know x is equal to 4, but I still need to find that corresponding value for y. So I'm going to go right back up to here and then replace that x with y, or replace that x with 4. So I would have y is equal to negative 1/2, replace x with 4. So that will give me half of 4 is 2, so negative 2 plus 4. So then y would equal 2. So if I was at the ordered pair 4, 2, that would give me the maximum area of that rectangle. And that's it.